Hello everyone, welcome back to Piperlium. It's been a while. It's been almost a year. I've been up to some things. Mostly projects, as always. So, with me being back, I want to make a series. Basically to adhere myself to regularly uploading pretty consistently, roughly once a week. And the project that I've decided to focus this on is called MAGPIE. Project MAGPIE is what I'm calling it. The Mars Atmospheric Ground Probe and Instrumentation Experiment. It's an experiment that is largely a feasibility study, so I'll be doing the design and the engineering of it, and likely creating a very, very rough engineering model. That way we can evaluate to see if the design was valid. This is part of a larger project, which is writing a paper on this. So with my previous project that was in a similar vein, it was my capstone project. I worked on a small sat in polar orbit, low Earth orbit also, and these are obviously going to be probes around Mars. So it's a completely different design environment, but roughly the same feasibility and design. So I've already gone decently into the project itself, where I have an extended abstract on my GitHub. I will post that there. It's going to be largely just a copy paste of the PDF, and feel free to read up on there. I will be posting all of my large version updates of my scripts, which, let's talk about the scripts. One of the things about doing this independently, I'm no longer in school. I have my degree in aerospace engineering, so it means I'm all on my own. I don't have access to big, large copyrighted programs anymore. I'm not using SDK for mission planning. I am using Python. I'm using Python with many, many libraries and many, many scripts. I will eventually post all of the large versions of the scripts to be public, and I may even combine them to make single functions to make them more efficient and easier for others to use. But we have to get to that stage first. And right now, everything is in the prototype, across the board. And that's okay. That means that all of my figures that I have in my extended abstract will likely change, because they were just back in the napkin math at the time. But as the deadline for this paper approaches, December 2nd, I will hold weekly videos talking about my updates and my thoughts about the project. They may not be on a camera like this, but they'll still be here. So, let's explain a little bit more about it. I'm gonna have to likely change my camera here, so stick with me. Okay, you may have noticed I've changed the angle. The quality is very different now. I'm on my laptop. It's far easier to kind of read my script this way. So basically, I think the easiest way to introduce this mission is imagine 6 tiny landers all scattered across Mars. Different latitudes, different longitudes. All recording weather, winds, and even possible lightning strikes all at the same time. That's kind of what the goal of MAGPIE is to measure weather across Mars in different places we've never landed before, at least successfully, and with the additional goal of doing it all at the same time. So to get there, we have an orbiter. As of right now, again, everything is subject to change. My scripts will be updated and be more accurate. My launch window may also change. Right now I have launched in late 2028 on a Falcon Heavy, the MAGPIE orbiter. It's basically our mothership. It'll do the main communication in between the Deep Space Network with a X-band antenna, and it has things like dual reaction wheels, so it's redundancy. Not like there are 2, there are technically 8 in the design right now, but it's a very redundant system. And it can generate 1.6 kilowatts of power at any given time in Mars orbit on average. So we have 6 probes. each right now around 20 kilograms, and they'll slam into Mars' atmosphere during reentry. They'll have their own retrograde package, which is yet to be named better, and these will be deployed from the orbiter, and they've got their own aeroshell, and the probe inside them will be deployed kind of differently from other landers, like you may be familiar with the airbag approach, or using the retrograde rockets for like the Mars Science Lander or Mars Science Lab. Sorry, this is a different approach. Pretty much, they're going to be in their heat shields, and then just do reentry, and then we deploy a parachute, a supersonic parachute. I believe it would be technically hypersonic. And then we'll fire retrograde rockets to slow down the craft. And it will still impact the ground using that parachute and the retrograde rockets. The retrograde rockets will not completely stop its vertical motion, neither will the parachute. Remember, we're on Mars, it's going to be a very thin atmosphere. So this is kind of adapted, kind of inspired by the Deep Space 2 probes, which were launched in 1999. They were much smaller at about 2.4 kilograms each, but they were impactors. They were designed to have no parachute, no retrograde rockets, merely survive the landing. They were unsuccessful, but I think the vein of having an extra probe, because they were originally actually with the Mars Polar lander, which also didn't work. But the idea of having this modular design that is cheaper and kind of simple and will be able to generate enough science all on its own, that's kind of what this got inspired from. So what are the sensors we're talking about on this probe? Very basic weather sensors, pressure, temperature, humidity, and CO2 levels. A solid state anemometer. We want to measure wind speed, but we can't guarantee that the probe will be upright, right? That'll obviously impact it. We don't want moving parts, and simple as that. Don't want moving parts. And what if it falls over? You want the wind to be unilateral. So we have a solid state anemometer. Basically, this works by putting out thermal load and then measuring that thermal load based on the takeaway using the reference known temperature. We'll have the ability to detect lightning, a microphone for any sounds, and we'll have two cameras, one called outcam and one called downcam. I think you can guess where they point. Downcam will be obviously recording during the reentry process to get an oversight view. This will be just generally useful to have a closer up image. And sidecam will be used for both descent and after we land. Additionally, sidecam will also have a thermal camera, a low resolution thermal camera, but it'll allow for us to give a little bit more sight on what is actually happening on the surface, especially at different latitudes. These probes can actually survive for longer. The other thing about the navigation package on these probes is there is an IMU, a radar altimeter, and a magnetometer. These on themselves are not that useful, but for knowing exactly where the probe is, it's far more useful. This allows for better comms. Speaking of, let's talk about power and communications. So the probes work on rechargeable. I didn't write that. I'm blanking. Apologies for that. Nickel metal hydride batteries we'll be using. Why not lithium ion? Lithium ion are great until you deal with bad temperature. Mars is going to be negative 60 degrees Celsius. That is cold, and lithium ions will die, and their charge output is very bad. So um, these nickel metal hydrides are much better than lithium in lower temperature. We'll also have solar panels, and the other thing is there will be an emergency battery. Sorry, kind of going all over the place, even though I've got a script right in front of me. It's a single-use battery, and actually it is an LTO battery, which is a single-use and is the same as the Deep Space 2 probes. It is basically the highest energy density primary battery out there. Primary battery just means that it can't be recharged in this case. For communications, we've got a redundant radio system for each one of the probes. We have the main, which is a home-built UHF system that will be able to deliver communication protocols much faster than our redundant, which is LoRa. Why is it LoRa? Well, it's simple. We're reducing the cost by reducing the complexity. If you can have an entire radio on one chip, it makes sense to do it that way, especially in these smaller probes. These probes are only about 30 centimeters in diameter. They're not large. The aeroshell will be about a meter wide. So why the probes? What's the goal of them? Well, they'll be able to capture dust storm electrification, polar frost cycles, ambient Mars sounds, basically data that is very hard to do with a rover. Because we can send these to Hell's Planta, that is a great basin that is super flat. We'll send Mars rovers there for sure in the future. I believe the Rosalind Franklin is scheduled to land there. But it's definitely going to be one of the sites we look at as people going to Mars, because simply it has caves. It could have water. It likely has lots of minerals. So it's a very interesting place. And going to the poles, for example, or Mount Olympus, are definitely very interesting opportunities. So, with that, we have 6 probes, and in the guidelines that you'll see on the GitHub, there are 5 landing sites. So we have 1 redundant. So we could either choose a new site if all the other probes are successful, or if one isn't successful or all of them aren't successful, we can just throw this one down again. And again, they'll always be recording all of their data and transmitting it to anything, really, because the UHF band is received by a lot of Mars orbiters, and so they could probably record all of the data as it's going. So if they don't survive re-entry or they don't survive landing, we'll still have some data from them. So with that, well, let's just kind of go a little bit off topic and talk about what I've been doing. So we have several scripts as of this moment. We have a power one, a communication, environmental reentry, so an EDL simulator that measures our control systems, our peak heating, our thrust that's given, everything. We also have what I call the orbital program, which gives us from our LEO insertion all the way to getting to Mars at our desired inclination of 120 degrees. With that, we use a kick stage right now in development, so it's all kind of a mess, but I really stress to try and read the documentation, call me out if something doesn't make sense, because I want to make this a very well-made mission. I've also got a 3D printer, and I'll be printing out a version of the probe to model. It won't be as strong as the aluminum version, which would be the flight version, but we can test as much as that we can. And so things like this this is the Gen 1 aeroshell. Yes, it looks very simple. It looks very basic. That's what it is. This is designed to be improved. This is based on preliminary design. You know, I don't have a very good version of the final design of the probe, nor do I of the aeroshell, or the orbiter, or the retrograde package. Is the retrograde package even a thing? Do I implement it into the aeroshell? These are things I need to figure out and consider. Now, I have months to do this. That's why we're doing it weekly. I will give you an update. It may not be a very good update, but it will be an update on this project. It could be small things from working on antennas for receiving, for testing this. It could be working on the actual engineering of these. Or it could be a very similar project like this, which is my weather balloon project. All of my projects, though, use very similar things, and so they can all kind of be interchanged. So with that, thank you very much for watching, and I hope you have a wonderful day. Thank you. Bye-bye.